Suppose that 70% of the people age 20, 24 have never smoked. Answer the following questions. So notice the way this is stated. Suppose it's asking you to believe that this number is the parameter, the true value. Clearly it's a proportion, and this is success. Success is a person in that age group has never smoked. What is the probability that in the sample of 100, so now we're sampling 100 from this population, we get a sample proportion of 65% or less, so our proportion is 0.65. Sample proportion. Are we sampling with or without replacement? Without replacement. I'm just assuming that we're going to do what normally is done, which is sample without replacement. We're not going to select the second person twice. Do we meet the 10% rule? Well, that's a good question. How big is this population? Suppose that 70% of the people aged never smoked. Notice the way this is stated, I'm assuming this could be the entire United States. I don't know, depending who's the author of this question. So if this applies to US, then N equaling 100 is much less than 10%. Okay. So yeah, we meet the criteria. I mean, even if it's not the United States, I suppose Oregon still meets the criteria. Again, 100 is nothing compared to a very large population. So we meet the 10% rule. We can pretend to sample without replacement, even though we're not. So for most national polls, that's what's happening. We're not going to sample the same person twice, but our sample size is tiny compared to the population size. Do we meet CLT? If you want to answer the question, what's the probability? We need to see if we meet the CLT, and we do, because 70% of 100 is 70, which is clearly bigger than 10, and then 30% of 100 is 30, which is again greater than 10. We are fine on that ground, so meet CLT, yes. That means we can't pretend. There's a lot of pretending, isn't there? We can't pretend distribution of p hat is normal. Don't forget, again, what the central limit theorem is stating, it's about the normality of this distribution. So we're going to do that. So our sample size is definitely big enough. We meet the CLT, great. That means then I can draw this picture, this normal distribution. This is all values of p hat that are possible. At the center of this is 0.7, which is E of p hat. Again, notice that I've used this symbol P because that is the chance of success. If I sample once, what's the chance that I'm going to find somebody that meets this criteria? Age 20, 24, and never smoked. The answer is 70%. And it happens to be the center of this distribution of all possible p hat values. And of course, I'm putting it here because I'm assuming it's unbiased. So it's an unbiased sampling method. So now I'm dealing again with the sampling distribution of proportions. Let's find the z-score, 0.65 minus the mean, which is 0.7. So notice the formulas are always the same. Measurement, the mean of all possible measurement, the standard deviation of all possible measurements. And I get this value. Okay. And notice this is not unusual. And why am I saying that? Because it's just about one standard deviation below the mean. So a little more, but not too much away. So that's not unusual. Let's actually calculate and figure out what not unusual then is in terms of a probability. So I'm calculating less than 0.65 if that's what I'm after. What's the probability that we sample 100? We get a sample proportion of 65% or less. So we're after this area here. That's a z-score. That is negative 1.09. Again, I'm running out of room, so I'll run like that. And now when I go here, though, I'm not going to round. I'm just going to enter that value, negative 1.09, 10895. Okay, and especially because I'm near 1, I should not be rounding because it's starting to matter here, and I need to go in the right direction, which is less than. Hopefully that did not change much. It did not. Okay, that's good. So I'm getting this value, 13.76, someone 13.76. And that is not unusual. Now you say that's a low probability. Yes, it is. But as we're going to find out, that's not considered unusual. Notice that that's just one standard deviation below, just a little more than one standard below the mean. And we know that between -1 and 1, that's about 68% of the data. And that is not a region that we consider unusual. We walked a little bit below that, but not far away enough. So that value is not unusual. When we get to 2 standard deviations away, that's when we're beginning the unusual region. And this is also depending on the situation, but definitely now we can start thinking about calling this unusual. And notice this value doesn't happen too often. Suppose that 70% of the people aged 2024 have never smoked. So back to this question. How unusual is it that we get 325 people aged 2024 or less out of a sample of 500 that have never smoked? So this is very similar or exact same question as before. And we established that P is equal to 0.7. And this time what's happening, looking at a p-hat value of 325, 500, when I calculate this, what does it come out to? 0.65. So looking at a p-hat value of 0.65, wait a minute, that is the same as in the previous question, 0.65. So here it was quoted as we're only sampling 100, 65% or less. Now we're sampling 500. We know that we meet the CLT, so let's not worry about that. After all, I've met it for 100, so now it's definitely going to meet it for 500. So I'm drawing my picture. Again, I really encourage you to do this every single time until this becomes automatic. As a matter of fact, I'm letting my hand move across this page, and this is just something automatic that I do. We know this is E of p hat. Again, notice that even though we increase the sample size, now is 500, this continues to be the same center. So this is true for any sample size. But what is it that we demand in order for this to be true? Unbiased sampling process. Notice I am not saying the sample we gather has to be unbiased. I'm saying the sampling process has to be unbiased because this distribution is based on everything that can happen, every single value. So it's the process that's generating this distribution with that center. What about the standard deviation? I'm going to calculate this. I didn't do it last time. I'm going to go here and type that in and see what we get. So the square root, then I go 0.7 times 0.3, divide that by 500, and I get 0.024939. What was it before? Notice that before our sample size was 100. So prior question N was 100. This is 500. Notice if I take 100 and quadruple it, it would be 400. This is slightly bigger than that. So what do I know? That when I quadruple the sample size, the variability will be cut in half. Now, it did go 100 more, but it's only if I quadruple it, it gets cut in half. So what is the prior standard deviation? I'm going to suggest that this prior standard deviation is approximately, well, let's double that. So it'll be around 0.04 something should have been the prior standard deviation. Let's find out. So go to the prior page and let's calculate the standard deviation for this question. All I'm going to do over here is just change it to 100. And sure enough, I get of course, a little more than double because I it did more than just quadruple. I added an extra 100, about 25% more. But notice, yeah, it's 4.5. So it gives me an idea, okay, what the variability is like. But what do I care about this? Because we're going to use this information to determine sample size. Why are we doing these questions? Because we want to show what is possible. Because the end game is not to do these questions, even though we're going to do later some questions like this for a very particular purpose. Right now, we're just getting to know the sampling distribution and how it behaves. But now that I've more than quadrupled the sample size, what we're going to show is that this value is going to become unusual to get. Before, what was the chance of that happening? 13%, and notice that was not unusual. But now the chance of getting this most likely is going to become unusual because I have increased the sample size. So the chance of that happening should have decreased. In other words, well, this picture doesn't look any different from what I drew earlier here. It has changed. This is now narrower, so that 0.65, it doesn't look anything like this. So in fact, if I try to draw it to scale, most likely it looks something. Well, let's see if I can actually do it. That 0.65 most likely now is like this. It doesn't cover as much area as before because it's been pushed out. This thing has got narrow. And that by narrow, you can see that the variability has been cut down more than half. So let's calculate this. Oh, I didn't do my z-score. I'll go over here. .65 minus 0.7. Square root of the fraction 0.7 times 0.3 divided by 500. Sure enough, I'm getting a very unusual value. Again, it's getting down to the very edge. So if this doesn't need to be that many decimal places, it's going to come out fine. Because tiny changes here now don't change the area by much. There's my previous value. And indeed, it is very unusual, 0.0073. That is less than 1%. So if I move, so that's 0.73% or 73 tens, hundreds, thousands, 10,000. The result like this would occur about 73 times in 10,000 attempts. Not very often. Can it happen? Of course, but it's less than 1% of the chance. So this is indeed very unusual.